My name is Kristen, and I was partners with Michael. This investigation is regarding collisions. Our investigation was kind of like the first one with the bouncing balls, but we wanted to see what would happen once it bounced twice. So what we did in the first investigation was if it bounced once, we saw the height that it came back up, but we wanted to look at the second bounce height as well. From our first experiment, we kind of saw that when you dropped it from about a meter, that it bounced back almost or around half of the height. So we were, part of our hypothesis was to see if the second bounce was half of the first bounce as well. So we wanted to make sure to test that. And then our second question was, let's say one of the balls does bounce half of the first bounce. Would it change if we had a different mass ball? So we did these trials with a tennis ball, which weighed 0.0552 kilograms. And then we had this experiment again with a soccer ball, which was 0.3739 kilograms. So obviously a difference in mass that is quite apparent. So we wanted to just see if our hypothesis was true. And we were just curious to see if the mass would affect it when it bounced. So what we did is we put a meter stick against the wall, and then we dropped the tennis ball first from 1 meter and watched it bounce the first height, which was about half, and then it bounced again for the second one. And to measure if it was possibly going to be this half of the first bounce, we used the app on the iPad that we've been using in class. And those pictures you'll see later in our video. They were a really nice representation of what it looked like, a bouncing ball. We were really happy with it. And we were surprised to see that it was pretty much half each time, give or take a couple centimeters. So with that being said, when we also were looking at the bounces, we wanted to look at the energy loss when the ball collides with the ground. Michael's going to go more into detail with the calculations we did and how we found out how much energy was lost. But overall, we did find that about half of the energy is lost each time that it is bounced. And obviously, the energy loss is different for the tennis ball, and it's different than the soccer ball. And that's because partially the mass and partially what the sound is when they collide with the ground, as well as the material that the ball is made out of. And we actually found that the tennis ball was more elastic than the soccer ball, which is pretty much expected. And it was more efficient bouncer, so it gave back more than just half of its height the first bounce. So that's what we thought made it more efficient. We did have a couple issues when running this experiment. Number one, just being able to kind of estimate the numbers of which it was bouncing back on the iPad, just because there aren't divisions of the number between 0.5 of a meter and 1 meter. We kind of had to guesstimate on our own. So our numbers aren't perfect, but they're in the ballpark. And number two, another error that we kind of experienced is when using the iPad app, it was hard because when the ball is dropping, you don't have a perfect vision of the ball. So when we were marking the points, we decided to mark it at the bottom of the ball each time. But when the ball is dropping and it's kind of like a fuzz, it's kind of hard to specifically mark the bottom of the ball. So that may cause some difference. But overall, that was pretty much what our experiment was about. And like I said, Michael will go into more detail about our calculations and what we concluded from it.
Michael Anderson, and I'm going to be talking about the data part of our lab and also some of the interpretations from the questions from Matt. So basically, like Kristen was describing, we took the tennis ball and the soccer ball again, and we wanted to study how the bouncing each time would lose some height, and kind of like what Matt asked in the questions, this is related to the energy of the system. So what happened was we would drop the ball and use the video physics app to measure the heights of the next two bounces, the maximum height. And what we got was, for the tennis ball, once we dropped it from a meter, it first bounced up to 0.6 meters, and then it bounced up to 0.35 meters the second time. For the soccer ball, if we dropped it at 1 meter, it bounced back up to 0.45 meters, and then the next bounce, the max height, was 0.22 meters. So what we can see from this is that the tennis ball is a lot more elastic and efficient than the soccer ball was at bouncing. What we wanted to do to interpret this data was to find the potential energy of each ball at its maximum height, and then because of that we could see how much energy was transferred away once it bounced. So what we did is we took the potential energy, which is the mass times the gravity times the height, and we would multiply those together for each maximum height. So when we did that, we found that obviously the tennis ball has less energy in it because it's smaller, has less mass, even though it's up at the same height. And the soccer ball, because it's a lot heavier, obviously has more potential energy. But what was interesting, and what we were interested in, was seeing how the energy was lost once it bounced off the floor. What we got was we would take the initial height, the 1 meter, we would multiply it by the gravity, acceleration of gravity, and multiply it by the mass, and we would take that and subtract the next bounce heights, the 0.6 meter one, we would subtract it. So what we discovered was that when we took the first energy from the first potential energy minus the second bounce's maximum height, we called this B naught and B1, or I called it that, and we got 0.54 Newton meters minus 0.325 Newton meters. So the difference is a little bit less than half for the tennis ball. That was the tennis ball. So what that means is that it lost less energy than it gained back. So it was more than 50% efficient at bouncing back up to the 1 meter height again. But of course it didn't make it all the way because it's not perfectly efficient.